Good afternoon. I've already filmed this lesson once and it seems to have been corrupted, so hopefully it'll work alright this time. So this is the end of binomial and into the normal distribution, which, pretty important bits. At the end, we almost finished binomial off last lesson. What we didn't do was talk about the expected value and the variance. So if you've got n trials and p is the probability of success, then q is the probability of failure, where q is the same as 1 minus p. I think we used the example of Conica shooting bow and arrow at a target, where the probability of success was 0.7 and the probability of failure therefore was 1 minus 0.7 or 0.3. So she's more likely to hit than to miss. The expected value, or the mean, mu, is often used for the mean, or the expected value of x, the expectation, they're all the same. It's just n times p. If Conica has 100 shots at the target and the probability of success is 0.7, I mean, the reality is she's going to get tighter and tighter and get worse, or, she realises that she's always heading to the right, so she moves further to the left. So they're not necessarily independent, but we are making the assumption that the result of each trial is independent of the others, and in most situations that would be close enough to true. So if she had 100 shots at the target and the probability of success is 0.7, then the expected value would be 70. That doesn't mean she would have 70, she might have 69, 68, 67, she might have 71, 72, 73, that would be just like if you toss a coin. If you toss a coin 100 times, the expected value would be 50 heads and 50 tails. Probably not going to be that, it's going to be 46 heads and 54 tails, or 51 heads and 49 tails. You've got a range of possible results that would fit in. It would be very unlikely to be 10 heads and 90 tails. You would expect it to be pretty close to that 50. Probably between 40 and 60 heads would be the most, would cover most times. If you did it 100 times and then did that lots and lots of times, that's a lot of coin tossing, then you would expect that most of the times you would get an answer. You might get 50 occasionally, but you'd get 45 heads or 53 heads or 41 heads or 59 heads, probably in that shape between 40 and 60. The variance is the spread of the results, and that becomes more important when we move on to the normal distribution shortly. So the variance is defined as n times p times q, or n times p times 1 minus p. I think the book shows it like that. I always see that as npq. They show it as np1 minus p, and that's fine. But that's the same as npq. The variance is equal to sigma squared, so that's sigma. Well, we were talking about sigma yesterday, as I think, where there was sigma, capital sigma, there's small sigma, and they're pretty different. But sigma is very frequently used to stand for the standard deviation. It's a measure of the spread. So variance is a measure of the spread of the results. For example, if we had, let's stick with Conica, we expect her to get 70, that she would, if she had 100 shots at the target, we'd expect her to get 70 hits. But sometimes she'll get a bit less, sometimes she'll get a bit more. And so would we be expecting something like that, where it goes up to 72 and down to 68? Or would we be expecting something, we're certainly expecting the mean of 70, would we be expecting something more like this, where it goes down to 60 and up to 80, for example. Alright? So this one would have a small variance, and this one would have And so, you know, the variance, again, sigma squared, where sigma is the standard deviation. And so, you know, in this case, you know, for Konica, N was 100, P was 0.7, Q was 0.3, therefore variance equals NPQ equals 100 times 0.7 is 70 times 0.3 is 21. Right? So 21, that means that sigma is equal to the square root of 21, which is, what's that, about 4.5 or something. Right? And so, if we've got a standard deviation of 4.5, we'll see with the normal distribution in a moment that we're expecting most results to be within about 3 standard deviations of the mean. So, you know, 4.5, another 4.5, and another 4.5. So we'd expect just about everything to be within about 13 or so of the mean. So that's not a bad diagram, that would you know, correspond to it pretty well. Okay, normal distribution. And this is used in lots and lots of situations. If you've got a big enough population, and so this might be something like the heights of people in Australia. It might be like the mass distribution of things coming from a factory. Where they're not all exactly the same, but there's a bit of variation. It certainly does apply to, if you get nuts and bolts and something, they're manufactured to be 3.72 centimetres, and but they might have a mean of 3.71 and a bit of a spread. So something, like this. It could be a whole range of different things, whether it's temperatures or weights or lengths or again heights of people. But what we get is a fairly symmetrical distribution. And we'll start with saying we've got a mean of 0 and a standard deviation of 1. So that's the standard normal distribution. That's the default one. We'll be using the calculator shortly for that. And so we've got about 3 to minus 3, so we've got just about everything fits into that range. So it's a lovely smooth curve, and Young, for example, is doing his IA on the coronavirus and how that curve has changed. In the papers they talk about flattening the curve. Flattening that presumably means it's going to spread out longer as well, but it means you haven't got the real peaks there. And it'll be interesting after the dust settles from this, to see the different shapes of curves, how some countries have, for example, lasted longer here, or it's gone up really quickly here and come down quickly. Lots of things to analyse. It's all very well when it's symmetrical there, and the formula of that is something like e to the negative x squared. So when x is 0, e to the negative 0 is e to the 0, which is 1. And then, as x squared gets bigger and bigger, when x is 1, when x is 2, when x is 3, you've got 1, 4, 9. E to the negative 1, e to the negative 4, e to the negative 9, it comes out and asymptotes to the axis. Of course, you've got constants there in front, so a e to the negative kx squared to make it higher, to make it spread out more or come in closer, and then you can move the whole thing along as well. So that's what your normal distribution looks like, and I guess the main thing is that it's symmetrical. Okay. Up until now, all of the distributions we've looked at have been discrete. what's the probability that Konica gets 5, hits the target 5 times? What's the probability of rolling a dice and getting a total of 10? What's the probability of tossing a coin 4 times and getting more heads than tails? Something like that. All right. So it's a discrete one where something occupies an actual value. But this is a continuous distribution, and so whatever it is, whether it's heights or something. So my height I think is 178, 179, but it could be 178.132. So there's a continuous range of heights, a continuous range of weights. And so what we're measuring here for a continuous distribution like this, the important factor is not the value along here, but the area. So the total area under this graph is going to be 1. The total area is going to be 1. And the probability of a certain thing is the area enclosed within here. So the area of that bit between -2 and -1 looks small. It's clearly less than a half. It might be around about 0.1 or something like that, perhaps. Yes, probably about 0.15 or something like that. We'll work that out in a moment. Okay. So the x value doesn't just take discrete values, it's continuous. The probability So the area shaded here represents the probability that we're between 2 and 1 standard deviations below the mean. 1 standard deviation, 2, 3, plus 1, plus 2, plus 3. So clearly it's a symmetrical thing. So let's work that one out and then we'll talk a bit more about the normal distribution. Okay, so when I was your age, a long time ago, we didn't have calculators like you did. In fact, in year 12, I got a calculator and it was like a big brick, and and that was quite a big step. But up until then, it was using. Well, I don't think it had normal distribution on it, and it certainly couldn't graph things like your calculators can do. And so I mainly used tables of logarithms, of normal distributions, and so on to work those out. But your calculator does that for you now. So grab a calculator. Okay. If you haven't got your calculator, pause this and then come back with your calculator turned on and charged. Okay. So it's the same as what we were doing to get into binomial. So you've got a menu down to probability, across to distributions, so that's 5, 5. And the distributions, again, stacks and stacks of distributions. Okay. We've got one normal PDF, two is normal CDF, and then way down was D and E, binomial, PDF, binomial, CDF. Okay. You need to understand the difference between those. We'll come back to the calculator in a moment. PDF, probability distribution function. CDF, cumulative. We can have another P there, cumulative probability distribution function. They're just calling it a cumulative distribution function. Similarly, probability distribution function, cumulative distribution function. You've used both of these, and so the PDF you use, what's the probability of rolling a dice 10 times and getting exactly 7 threes? Okay? So, yeah, it was tossing a coin and getting exactly 7 hits, something like that. The CDF was, getting, a range from 5 to 7, or from nothing up to 7, or whatever you want there as a as a range. So you're using both of those, the PDF and the CDF. For the normal, the PDF gives you the value on there. You don't want that. You are never going to use the normal PDF. But the CDF gives you from here to here, or from here to here, and whatever. Okay? So, in order to find this, so we're going to use the normal CDF. In your calculator, let's go to the normal CDF. So, normal CDF. And you'll notice in the box it gives you the lower bound, the upper bound, and then mu and sigma. The default that's already there is 0 and 1. So they're saying lower, upper, mu and sigma. The default is 0 and 1. You can change that if you want. To start with, we'll just use the 0 and 1. So that's the standard normal distribution. Well, I'm going to go from -2 to -1. My estimate in that, so just looking now, I've got a half above and a half below. It's only a pretty small fraction of that half. I'm guessing about 0.15, but we'll see what it is. So I want lower -2, upper -1. So plug that in. -2, -1. Oops. And 0.1359. so 0.136. My estimate is 0.15 or 15%. That's okay. Okay. You've got normal distribution. I want to know between -1 and 1. What's the probability that something is within 1 standard deviation of the mean? So this is normal, with an arrow, we show that as 0, 1, and then we want to go from -1 to 1. So that's a normal distribution of mean 0, standard deviation 1, from -1 to 1. In your calculator, you're putting them in a slightly different order. So, it's sort of important to have this bit of a feel for what's happening. So here we go again to the menu. Probability, distributions, 5, 5, normal CDF, and to have a fair idea of what's going on. Not sure how accurate my diagram is. I think it probably comes down a bit steeper than that because we actually end up, that looks like a about half overall. It's actually more like 2/3. So if we feed that in from -1 to 1, 0 and 1, we get up with 0.682. So that means that approximately 68% within one standard deviation of the mean. You have 2/3, just over 2/3. What about within 2 standard deviations of the mean? 1, 2, 2. Okay. So now on normal distribution, 0, 1, -2 and 2. Right, let's feed that in. 552 we can say. And we get from -2 to 2, still 0 and 1. And we get 95.45. So let's say 0.9545, so 955. So we'll say approximately 95% within 2 standard deviations of the mean. And now with the 3 standard deviations, clearly that's almost everything. And that was a comment I made earlier that most readings, most people, most of the standard, the bolts or washers or whatever they are, lie within 3 standard deviations of the mean. Alright, let's work it out. So that's from -3 to 3, and we've got 0.9973. So 99.7% within 3 standard deviations of the mean. Alright, so just looking at other bits, what's the probability? What's probability there? Probability that x is greater than 0. What's the probability that x... Oops, that's not very well drawn. That one, no? What's the probability that 0 is less than x is less than 1? And I want you to do these without using your calculator. There's enough information on what you've already done without using your calculator. What about, and by all means check it with your calculator. I can't get that in the middle there. Again, there's the middle. So that was 1, that was 2, so let's try again, 1, something like that. Let's go between, -1 and 2. So the probability -1 is less than x is less than 2 equals, right? Have a go at those without using your calculator. Alright? Maybe, just pause for a moment and then we'll come back and have a go at those. Okay, we're back. pause or not? You're still there, right? So probably the x is greater than 0, I mean, hopefully just from the symmetry there, you understand that that's 0.5, 0.500 if you like, either would be fine. So there's half above and half below, there must be. The probability that you are bigger than the mean. Right? In this case, we have to have a mean of 0, but that won't necessarily be the case. Probability that 0 is less than x is less than 1. Alright, I'm working from this one here. Again, we've got 0.682 between -1 and 1. So there's half of that in between 0 and 1, or between -1 and 0. So it's a half of 0.682. A half times 0.682, so it becomes 0.341. If I draw my diagram accurately, does that look like a third? Does it look like 2/3 of that one? Probably not. Probably needs to come down a bit more sharply there, but it's not bad. And so get used to drawing that. In most of the questions, I would be drawing that sort of sketch just to get a feel for, is it above the mean, is it below the mean, is it a big section, is it a small section? So, just to be drawing that sort of normal distribution shape. Probably the -1 is less than x is less than 2. Alright. Here's from -2 to 2. So, clearly this bit is the same as this bit. So I've got 0.341 here, and then a bigger bit here. The bigger bit there will be half of this one from -2 to 2. So half of that, what's that going to be? 478, I think. Plus 478. What's making the noise there? Don't tell me there's something wrong with this camera again. I'm going to be very annoyed if I've done this twice when it hasn't worked over time. Okay. I've added up this bit plus this bit, gives me, I think, 0.819. And again, by all means, check that with your calculator. And the last digit might be out or something just from the rounding off, but that would be close enough. All right. Alright, so I guess the only thing then is to apply it to a more realistic situation. And I'm going to say that, distribution of heights is really interesting. So, some people clearly are taller than others. I think I'm fairly average height, maybe a bit taller than average. Some people are taller than me, some people are shorter than me. And it'd be interesting to compare different countries. For example, I think in parts of Africa the average height is quite low, in parts of Asia the average height is quite low, whereas you look at somewhere like Holland, the Netherlands, I think that's the country which has the tallest average people. But if we say height is normally distributed with mean of, I'm going to say 170 centimetres and standard deviation of 10 centimetres. That means that almost everyone, 99.7%, would be between 140 and 200. I don't know too many people outside that range. Certainly some of the league footballers, 200 centimetres, so they're above 200 centimetres. Some, basketballs in America, China and so on are more than 200 centimetres. There are some people who are shorter than 140. So it doesn't mean it can't happen, but that means, that would be 3 out of 1,000, or, in our school, 300 or 400. 1 out of, it doesn't really count with kids, does it? Some of the kids would certainly be shorter, so that maybe not a good example. So I talk about adults, alright? So, probability of between, let's say, 180 to 190 centimetres. Alright, quick sketch of this. So it's a mean of 170, and that goes up to 200 and down to 140. Okay, there's a bit of a sketch there. I want to go, where's 180, there's 190. this much here. Right. So, again, using your calculator. Okay. 5, 5, 2. So I've got a normal CDF. Again, you know, PDF, not going to use that for normal. Binomial, you use both. Normal, just the CDF. Okay. Lower bound, 180. Upper bound, 190. Mu, 170, the mean. Standard deviation, 10. Oh. And I've pushed the wrong button. Try that again. $170, 10, and I want, I was going to do something else with you, but let's just get the answer. Done it wrong again. Somehow I filled in 70 rather than 170. Okay. If at first you don't succeed, give up. 552. Lower bound, 180. Everyone still awake out there or not? Upper bound, 190. Mean is 170, not 70. Standard deviation is 10. And here's our answer. Alright, what are we expecting? Well, in fact, what I could just do is take this one, which is from 0 to 2. So half of this one was 0.477, 478. Take away half of this one, which is 0.341. That should give it, shouldn't it? You know, that much there between 1 and 2. So that should give us 0.1137. 135? No, 136. Okay, so 0.136. And so I reckon that'll do us for today. There's a couple of quite tricky questions in the in the chapter there, but there's a lot of questions at the end there. Note that the probability that x equals 170. Well, let's make it something else. 180. What do we mean by that? Do we mean that that's the closest? The probability that someone is exactly 180 centimetres is 0. The probability of a specific value, because there's no area to it. We could say from 179.5 to 180.5, and that would be a reasonable interpretation of that. And if I said, that 180 is less than x is less than 190. Sometimes, if we put in equals there, it's not going to change it, all right? 180 less than x less than 190 is the same as 180 less than or equal to x less than 90, because, the actual value of 180 has no probability associated with it unless we extend it to that. And the question would need to make that clear if you were going to round off to the nearest whole number or something. So there's a few questions in the exercise that involve equal to as well. Okay, hopefully this is recorded.